Now moving on to Chapter 3, we're going to discuss very important applications of interpolation and curve fitting that definitely occur in many scientific applications. To start off, we want to make sure we understand the difference between these two terms. We're looking at how data can be modeled by curves. And first of all, with interpolation, the idea is that given data points, we would like to construct a curve that fits those data points. And then our major assumption in this case is that the data points, as indicated as I filled in the blanks of your notes, the data points are distinct. That means there's nothing that repeats. There's no duplications. And that the data points themselves are accurate, depending upon how they were recorded from an analog device or human, whatever. We're assuming that the data points are accurate. So the point is just to find a curve that would fit to describe how the data might look in general. Curve fitting, on the other hand, is the idea of finding a smooth curve that approximates the data points. Because in this particular case, the assumption is that the data has what we call noise, or that there are errors in the measurement. So we don't assume that the data points are accurate in that case. So we're just trying to get a curve that somehow approximates the data, but doesn't necessarily have to fit the data exactly because we're not sure the data itself is correct. Next slide here, we actually draw a picture that sort of indicates the difference between these two techniques. So on this Cartesian coordinate system of x, y, assuming x is an independent variable and y is a dependent variable that might define some function of the data, let's suppose that the three red points there that you see on the Cartesian coordinates is the data, and the green curve and the blue curve represent the two different approaches we're talking about. So the green curve is an illustration of interpolation. The fact that that green curve actually passes through those three data points. Again, assuming that the data is perfectly accurate and there's no duplications. In other words, each one of those x coordinates is completely different. The blue, which almost looks like a straight line here, is an illustration of curve fitting, where again, we're not assuming the data is accurate. We just want to try to get some sense of the trends of the data. In this case, it almost looks like they're sort of linear. So that's why the blue curve does not go through the data itself. It sort of represents a monotonically increasing function there that might describe the trend of that data. So both of these approaches is a way of estimating what this function, if we represent it as y of x, would be given, say, n+1 data points, and we'll index them with the subscript I running from 0, 1 up through n. So for every x, there would be a y. And if it is a function, then we also know that for every x, there's a unique y, if we think of this as defining some function. So our goal is to either produce a smooth curve through those data points for curve fitting, or to actually find an interpolant. In other words, another function that would actually fit through that data. In either case, we could use the function either from curve fitting or interpolation to perhaps predict values that we don't know, which might lie farther out on the x-axis. And we'd like to know, given what we know from the data that we have, what might the future hold if we have some confidence that this function describes the data. So in the next section, we're actually going to use a technique to construct an interpolating polynomial. And this is called Lagrange's method, named for the French mathematician Lagrange. The goal is to construct a unique polynomial of degree n that passes through the n+1 distinct data points. Now the first thing I want you to pay attention to is notice the degree of the polynomial is n passing through n+1 data points. So the degree of the polynomial will always be one less than the number of data points, or the reverse, we could say the number of data points will be one more than the degree. That should make sense to you because if I gave you 2 points, you could fit a unique line through it. If I gave you 3 points, you could fit a unique quadratic, and so forth. So that should make some intuitive sense. Lagrange's method is based on this very simple formula, as indicated here. The representation is for a polynomial p, subscript n. Again, the subscript reflects the degree. So if n is 1, it would be a linear or a straight line. If it was 2, it would be a quadratic. If it was 3, it would be a cubic function, and so forth. So p of n of x is given by a summation. Notice again very carefully, the indexing of I will run from 0 to n. That's a total of n plus 1 indices to reflect the n plus 1 distinct data points. The summation is with your y coordinates of all your data points. Keep in mind all the data points are of the form xi, comma yi. So the x of i's is the x coordinate, the y's of i's is the y coordinate. Thinking of a Cartesian coordinate system in 2D. So the summation is given by the y coordinates multiplied by a function. The function is called Li of x, and notice the subscript matches the subscript of the y. So to some extent we say that these y coordinates are weights on each one of these functions. So when you sum up all these functions, Li of x, weighted by the y coordinates of the data itself, you construct a polynomial. So the question is what are these very special functions called Li of x? First of all, they're called each one of them, the ith one is called the ith cardinal function. The formula for the ith cardinal function is given here. It's a simple product. It's a product of these terms, x minus xj divided by xi minus xj. Now, what are these xi's and xj's? Remember, those are particular x coordinates of the data. And x is just your independent variable. Okay. So in each case, I will run from 0 to 1 n, but j is the index of the multiplication of the product factor here. J will run from 0 to n, but j will not be equal to I. Okay. So in this case, that makes sense because we're going to do xi minus xj. If I could be j, then we're going to be in big trouble. All right. So we'll see what these, how these particular forms will work in just a minute with an example. But it's just a simple product of these monomial terms, x minus xj, over these scalars. Xi minus xj are just scalar values that are determined from your x coordinates of your data. And the numerator terms are just going to be products of, say, x minus x0 times x minus x1 times x minus x2 and so forth. All right? As long as j doesn't match the I. J cannot match the subscript on the cardinal function. It can run from 0 to n, but it can never be the I. So for L0 of x, j will never be 0. For L1 of x, j will never be 1. For L2 of x, j will never be 2. And so forth. So let's look at the very simple case of just 2 data points. They're represented here as x0, comma y0, and x1, comma y1. And so our goal is to construct a unique polynomial, fit those 2 data points. Again, the degree will be 1 less than the number of data points, so we're looking at producing p1 of x, which is just going to be a linear function, a straight line. And by Lagrange's method, it'll be of the form y0 times L0 of x plus y1 times L1 of x. Again, the cardinal functions multiplied by their corresponding y coordinates of those subscripts. So again, the y0 would be known, the y1 would be known, that's from the data itself. So we just need to define those cardinal functions. Here's the 0th cardinal function, and here's the L1 of x cardinal function. Keep in mind they're all product terms, but in each case because P1 of x is linear, each one of these will be linear. So that's very, very important. If we're summing all these up, then the degree of each one of the cardinal functions will match what we're trying to construct. So that'll make it a little bit easier for you. For P1 of x, L0 of x is linear, L1 of x is linear. For P2 of x, L0 of x would be a quadratic, and L1 of x would be a quadratic. So we would know how many product terms we would have. There's only 2 data points, so L0 of x will have to be of the form x minus x1 over x0 minus x1. Remember, the j can't be equal to 0. This is the j term. And L1 of x, j can't be equal to 0, so, it cannot be equal to 1, excuse me, so the form will be x minus x0 over x1 minus x0. So what you can think of, these terms on the right here, to the right of the subtraction sign, will always be the other subscript. They're the opposite of what we have. Instead of L1 of x, you have x0s here, and for L0's x, you have x1's here. Okay. Just remind, it's all the products that you can take with the other coordinates, but the j can never match the subscript of the cardinal function. So that's just using the formula. That's all we're doing. Okay? And each one of them would be linear. So if you go back to the formula we had a minute ago, again, we're just evaluating this particular product form. In this case, the j will go from 0 to n, and the n is just equal to 1 because there's only 2 data points. Okay? Let's go back to our current slide. Then we can ask the question, all right, if those are the 2 cardinal functions, each of them linear, to construct the linear interpolant to both of the 2 data points, what do we know about P1 of x0, and what do we know about P1 of x1? In other words, when we plug in x0 to P1 of x, if this is a interpolating polynomial, then what you should get back is y0. It fits the data. That's what we mean. And when I plug in x1, I should get back y1. Okay? Well, let's see if in fact that is true. Given the formula that we have above, if you were to evaluate P1 of x0 and then put it into the Lagrange formula we have up there, we would get y0 times L0 of x0 plus y1 times L1 of x0. Now look at the 2 forms of the cardinal functions you have above. Here's L0 of x and here's L1 of x. Again, the y0 is the y-coordinate of the first data point. When you plug in x0 up here into L0 of x, what would you get? Well, remember, these are constants that we already know about from the coordinates themselves. You're just going to plug it into that first component there. So when x0 goes in for this x, you're going to get a 1 back. So this is going to evaluate to 1. But when you plug in x0 into the other cardinal function, you can see what immediately is going to happen. The numerator will go to 0, and this will be 0. So what's interesting is that when you plug in the x coordinate that matches the subscript of the cardinal function, you get back a 1. But if they don't match, you're going to get a 0. So we're going to have y0 times 1 plus y1 times 0, and guess what comes back? y0. So that means this interpolates to the data point. It actually goes through that data. Now let's do the same check for P1 evaluated at x1. Again, that would mean we would evaluate y0 times L0 of x1 plus, again, go back up to this formula right up here, y1 times L1 of x1. Okay. And using almost the same logic we had before, when you plug x1 into the 0th cardinal function, you're going to get a 0 back. When the subscript of the cardinal function does not match the subscript of the x-coordinate, this will be 0. But when they do match, in this case, when you plug in x1 here into L1 of x, you're going to get a 1 back. And so this will evaluate to 1. So the first term goes away, and this will be y1. So this is a very simple example that demonstrates that the Lagrange formula works just fine when you have just 2 data points. This P1 of x constructed in this way would be the line that would fit through those 2 points. Now, I know this seems awfully complicated for 2 data points, but the process is the same as you have more and more data points. And so it's very easy to write a code. It's very easy to write an algorithm to do this for any number of data points. And so it's a very simple method to construct an interpolating polynomial. For 3 data points, it gets a little bit more complicated. So in the next slide, we've illustrated this by the 3 data points x0, y0, x1, y1, and x2, y2. Again, Lagrange interpolating formula would be for P2 of x, again, 3 data points. Unique polynomial fits it as of degree 2, 1 less than 3. So here's the general formula for P2 of x. You take each one of your y coordinates and then multiply them by the corresponding cardinal function. Again, we've seen this definition before. The only thing I'm filling in the blanks for you now is what do the cardinal functions look like for a quadratic interpolating polynomial. Well, like I said earlier, if the degree of this P2, if P of x here is degree 2, each one of these cardinal functions will be quadratic. They're constructed by the products of these differences. So L0 of x, remember that means j can never be equal to 0. So in this case you'll have x minus x1, x minus x2. You're missing the x minus x0 term. And then if you can remember how the numerator is constructed, then the denominator term is the same as the top. You just put in x0, the index of the cardinal function in the bottom. Notice this pattern again. Then for the L1 of x cardinal function, again, j can't be equal to 1, so you'll have x minus x0 times x minus x2. You don't see an x minus x1 term. And then in the denominator, you just sort of use the same general form of the numerator, but you plug in the coordinate x1 and x1 in both of them. So the denominator terms are just scalars. And then L2 of x, again, j can't be equal to 1, so you'd have x minus x0 times x minus, it can't be equal to 2, it's x minus x0 times x minus x1, and then you plug in the 2 in the bottom. Each one of those cardinal functions is quadratic. You add them up, you're still going to get a quadratic, but remember you scale each one of them, or you multiply each one of them by the corresponding ith coordinate. So what type of curve is P2 of x? Of course, it's a quadratic. But also, the same is true for each of the ith cardinal functions. So this representation of plugging in an x-coordinate into a cardinal function could be described as indicated here in terms of L sub I of xj. It turns out you could specify that as what is known in mathematics as the Kronecker delta function. In other words, that Li of xj is, from the way we've been constructing it, equivalent to what is called delta ij, and the Kronecker delta function ij will always be 0 if the subscripts do not match. If they do match, the Kronecker delta is equal to 1. And that's exactly what we're doing as we build a Lagrange interpolate. When we plug in an x-coordinate that matches the index of the cardinal function, we get a 1 back. Otherwise, it's always 0. So sometimes you'll see this mathematically written that the evaluation of the ith cardinal function is described by the Kronecker delta. So I'm going to draw a picture to illustrate what these cardinal functions look like as we take the linear combinations of them to construct the appropriate unique interpolating polynomial. If we did that for this particular case of x0 being 0, x1 being 2, and x2 being 3, those are just the x coordinates. So we haven't said anything about the y coordinates. That's not really what I'm going to draw. Just simply want to see what these cardinal functions look like. And they're completely determined by the x coordinates. So I'll say that again. The ith cardinal functions, all of them, L0 through however many you have for the particular polynomial you're evaluating, are completely determined from the x coordinates by definition. The y coordinates are simply used as weights in the Lagrange formula. So for this particular case, if those are the x coordinates, here's what L0 of x will be. Again, there's 3 data points, so each one of the cardinal functions will be quadratic because we're summing up all of them to produce a quadratic polynomial. Again, the numerator term will involve subtracting from x all the other x coordinates other than the 0th one. So in this case, we'll have x minus x2 times x minus x3, and then we plug in x0 into those for the denominator term and evaluate those numbers. So you'll have 0 minus 2, hence minus 2. We'll have 0 minus 3, hence minus 3. So the denominator term is going to be a 6, and so this is exactly what we would have for L0 of x. And you could, of course, factor those. I mean, you could multiply those apart and get a form of, a form of the x squared minus 5x plus 6 and all that divided by 6 if you wanted to. But it's fine to leave it in that form. L1 of x, again, j cannot be equal to 1 in this case, so we are not going to have an x minus 2 term, so we'll have x minus 0, which is just x, times x minus 3 on the top. And then we'll just plug in x1, in this case is 2, into each of those for the denominator term. Wherever we see an x, we'll plug in the 2. So we'll have a 2 here, because that's just x minus 0, or 2 minus 0. And then 2 minus 3 is minus 1 here. And we'll take the product, and that's negative 2. So another way, and then multiplying through, we could represent L1 of x as this quadratic. And then finally, L2 of x, of course, j can't be equal to 3, so that we can't have an x minus 3 term, so we'll have x minus 0 times x minus 2. And the denominator term is the same form. You just plug in the x2 value in for x. That's supposed to be 3, so you'll have 3 times 3 minus 2, which is 1. And again, you could simplify it if you want, multiply through by x on the numerator term, and that is the quadratic. So those are the 3 quadratic cardinal functions that we take linear combinations of with the appropriate y coordinates that you give me to construct a unique quadratic interpolating polynomial that'll fit the data. So what I've done now is I've actually sketched a rough diagram of what each of the cardinal functions will look like. This is just a rough sketch, but first thing to notice, I've indicated the horizontal line for all the y coordinates here being 1, indicated here. This is a scale from 0 to 1. And then what I've done is I've ticked off the value 1, 2, and 3 for the x coordinates. So again, L0 of x, if you plug in x0, you should get a 1 back. So it starts here. But it's going to be 0 at x1 and it's going to be 0 at x3. So it'll pass through each of those x coordinates with on the x-axis. It'll be 0 at both of those, but 1 at the first one, and it'll have a quadratic shape. And again, it would keep coming back up here, but I don't need. We're only interested on interpolating on the data that we're given, so we don't need to go past 3. x2 equals 3. For L1 of x, it's a quadratic, but remember, it's going to only take on the value 1 at the subscript 1 for the x-coordinates, which means the second data point, x1 equals 2. So it's 0 at all the other ones, but it's 1 there, and hence it has this particular shape, as we see here. And then L2 of x can only be 1 when you plug in x2, so that's at the x-coordinate of 3, and it's 0 for the other two x-coordinates. So again, notice its shape. So again, you take the linear combinations of these cardinal functions weighted by the appropriate the y coordinates, and you will construct an interpolant which will always fit the data. But you can see sort of in general that the cardinal functions take on different ranges of values between 0 and 1, but what's important is where are they 1 and where are they 0. So they're only going to be 1 on the subscript that matches their index. So in general, as indicated in the next slide, we ask the question, does the nth degree Lagrange polynomial interpolate n+1 data points? And the answer is yes. As indicated by the formula that you see, we had Pn of xj would be the same as the summation of yi times li of xj. That's just the formula we've always used before. But remember that another name for li of xj is the Kronecker delta, which can only be equal to 1 when the subscripts match. So if they match, that would be that j would be the same as I, that would be equal to 1, and we would get that if I is j equal to the index I is equal to j, then we would have yj. So then therefore Pn of xj will always be equal to yj, which is what we mean by interpolation, that when you plug in the x-coordinate, you will always get the y-coordinate back. The function will fit through all the data. Now you can prove, this is not in 370, we do this, but if you go on to take Math 471, 472 series, this could be one of the proofs you work on in that advanced numerical mathematics course in the math department, is you could ask, well, what is the error for approximating a function f of x by a polynomial, an interpolating polynomial constructed using Lagrange's method? And so we could represent that error as here is what's the difference between the function and Pn of x and for those n+1 data points. And what I've written for you is the formal representation of what that error is. It's simply represented by, it's a function of this form, x times x0, x minus x1. All the x coordinates appear, that product. So the error itself is a function, is what we're saying. And this is the description of it. It will be of degree n, matching Pn of x. And the denominator term will be n+1 factorial. But that will be multiplied by this term, which is the nth plus first derivative of f of x, evaluated at some interior point. So this is the Greek letter c, and the c is somewhere between x0 and n. So we'll say we will say that this is an interior point to the interval of interest for our interpolation. So so the error is controlled certainly by of how many terms you have up here in terms of the degree of the polynomial you're using to fit it, but also by the derivative. So if the derivative is well bounded, then this might not be too bad. But if the derivative could get very large, then you could run into trouble in terms of the error. So the degree really does matter. The problem is that these kinds of polynomials are going to oscillate a lot and can generate a lot of errors in between the data. It will fit the data, yes, but the oscillations that are going to occur because of these multiplicative factors is going to perhaps be problematic. So this is something that we're going to be looking for, is that can we do better? The advantage of Lagrange's method is that it's very simple. It's very simple to program this. You can imagine the very simple loops it would take to generate this Pn to construct and then evaluate the Lagrange polynomial. But if you keep taking larger and larger data points, if n got to be very large, thousands of data points, clearly you don't want to have a 1,000-degree polynomial. That is going to have severe oscillation problems in trying to represent any type of real trend in the data. So we need something more efficient than Lagrange's method. Yes, it's simple, probably would work well when you have just a handful of data points, just a very small number of data points, but it's not going to work very efficiently when you have a large number of data points. So that'll be the topic of the next lecture, where we'll consider what is called Newton's method.